Can you hear? Hello? I heard. All right, everyone. Thank you for being here today. I'm very excited to introduce our guest speaker, Dr. Luis Ocampo Giraldo. Luis received his PhD in nuclear engineering at Penn State and also spent some time at Brookhaven Labs. But he found himself at Idaho National Lab, where he currently serves several critical roles under the Nuclear Nonproliferation Division over at INO. And recently, Luis and his team were also recipients of a R&D 100 award, which is a pretty prestigious award. For his project Tripwire. For those who don't know, Tripwire is a first of its kind radiation monitoring system that is used to detect radiation over large and inaccessible areas such as nuclear waste repositories. So congratulations for that, Luis. Outside of science, outside of the science as part of Luis's day-to-day, he's heavily involved with mentorship. He is actively involved with the GEM fellowship program at INL, and he also takes on several interns during the summers. This past summer, out of a few hundred mentors and the 700 interns, Luis was the runner-up for the 2024 INL Mentor of the Year award. It really speaks to Luis's character and the kind of scientist that he is. And these are just parts of the reason as to why we're excited to have him here today. So everyone, please join me in welcoming Dr. Luis Ocampo Giraldo.
Good morning, everybody. Thank you for being here. Thank you for the invitation. It's a pleasure and an honor for me to come and speak with you. Several years ago, as you will hear from my journey, never did I expect to be called Dr. Luis Ocampo Giraldo. Never did I expect to win an R&D 100 award, to have a patent, et cetera, et cetera, et cetera. So it's very, very moving for me to be here, and I thank you for being here to share this moment with me. Today's presentation, as I was trying to put it together, I went back to all the colloquia that I participated on. And I was often faced with a lot of people who would come and say, I'm so-and-so, and I've had 30 years of experience running a power plant. I'm so-and-so, and I've had 20 years of experience in the government. But nobody really talked about how they got there. What was the journey, right? And they felt like, well, ultimately, that'll be me one day. But in 30 years, like, that's a long time. How do you get there? What's that process? And so I wanted to cover with my presentation, my journey. I wanted to share that with you because in my experience, there's not many people that look like me. And it was a very, very large struggle for me throughout my entire career, even between undergrad or just trying to find a degree in undergrad to actually major in, to find somebody that looked like me. And that's okay. That's part of the fabric of our nation. That's where we are today. But in the first part of the presentation, I want to share with you that journey. What was that like? And by no means is this the perfect journey. This is not meant to be a guidebook for you to emulate. It's to offer an empirical data point. So if you ever wonder, how does somebody get to whatever? Well, this is my story, and you can use that for whatever it's worth. Maybe it's instrumental to you, but it's an empirical point that might serve to guide your journey. Then the second part of the presentation is focused on some of the projects, one of them being Tripwire. Thank you for mentioning that. Several projects which you will see are not necessarily hand in hand, the same, scientist or the same researcher leader for them, but I am that researcher and I participate on them. I don't lead all of them, I co-lead some of them, I contribute to all of them, and I lead several of them. But I want you to see what ultimately your life could be like if you choose to join a national lab, if you want to do cutting edge research, because we don't often talk about what that life is like. We don't often learn about, what really is going on at the national labs. Sometimes we hear about, people winning Nobel Prizes and they are the national labs and such, but what's the day-to-day like? And I want to offer a little bit of a perspective into that. So with that, let's begin with usted quién es, right? And who are you? So I was born in Armenia, Colombia, South America, the north of South America. I graduated high school in New Jersey, Morristown, New Jersey. And then because of a program that they offered, they brought me in to really consider going to Penn State, and I loved it. They showed every single day a different engineering at Penn State. And that Thursday, they showed the nuclear reactor. Penn State is very fortunate to have a trickle reactor that's an open pool reactor, and you can see inside of it, and they pulse it. When they pulse the reactor, they make it go critical, by design, it shuts itself off. And when it shuts itself off, you get shrink-up radiation, which is this blue glow that you've seen in pictures, but I guarantee you, the picture does not do it justice. Seeing it in person was the most life-changing moment for me because I was going to be a chemical engineer. I was good at chemistry. And then I saw that and I was like, this is fascinating. I need to do this. This is my life. And that was the day that I decided to become a nuclear engineer. Long story short, I did my undergraduate. I participated in SHEP, we were president of SHEP, et cetera, et cetera, et cetera. And then I was also exposed to the Magneto Scholarships Program, which is a program that's kind of like a summer research initiative where I was allowed to do research over the summer. And it was also, you know, life-changing, but it wasn't so that I decided to do research right away. But that was the seed that exposed me to what research was all about. So from then, I decided that I needed to get a job because I was tired of being broke as an undergraduate student. And so then I said, well, I should just get a job on something that I'm good at. Turns out I was decent. I was pretty good at thermodynamic modeling. And I said, well, I should just go do that. Turns out I can't do that for more than one day because it's just not exciting to me. And that told me a lot about myself. The first thing is that just because you're really good at it doesn't mean that that should be your career, right? That doesn't mean that that's what's exciting to you every single day to wake up and keep on doing it and make you passionate about that work. And we need to learn to differentiate that. I didn't do that and it cost me dearly. Obviously, it was a learning experience and it's way behind me. But I wish that I had thought about it some more because I don't know, I found myself in a very sad place because I wasn't happy with my journey that after all those 4 years, which were incredible, now I found myself very sad in doing a job that I wasn't fulfilled by, right? So fulfillment was a big thing for me. So then I decided that I should go get a master's degree. So then I called back Penn State and I said, I would like to go back. They said, well, why don't you come check it out? Let's do something in maybe nonproliferation. It was a new program at the time that was being put together. Through a participation in a society, the Institute of Nuclear Materials Management, they allowed us to come to Brookhaven to just check it out, kind of like a visit. And in that visit, I learned about Brookhaven. Brookhaven is one of the 17 national labs in the complex, and they're very famous for high energy physics. So here is a picture of me riding a tricycle, which you need to do if you're going to be at the National Synchrotron Light Source, the brightest light source in the planet. It's so large that you need a tricycle to get around because it just takes too long to walk around the whole thing. So that was really neat. But because of that participation, they invited me to, or they let me participate in a summer internship program, which was my first summer internship in what I would call my new role as, you know, a nuclear engineer in nonproliferation, right? No longer into the world that I left behind because now it's way behind me and I don't really talk about it because I don't want anybody to ask me thermodynamic questions ever again. But in my new role, it turns out, I actually won an award for that paper that I published, that I wrote that summer, which really was a clicking moment for me because then I realized, you know, I like this, I'm good at it, clearly. This is something that I should pursue. So that was like the green light to keep on pushing forward. Along that journey, somebody told me you should consider getting a PhD. And I said, no, I shouldn't. And they said, no, really? I mean, you have done like half the legwork already with the coursework. And you're good at this, and I think this is, you know, you're passionate about it. This is something for you. You should consider it. Along that same time, I came across the GEM Consortium. So it's kind of like a lot of things just came together. And then I said to myself, well, if I am meant to get a PhD, then I must pass the candidates exam. So I took the exam. I started really hard, and it turns out I passed. And it felt like a kismet moment where it was like, this is it. It's meant to be. I should get a PhD. So then now I have finished my master's. I am going into my PhD as a PhD candidate officially. Now I'm a GEM fellow through Brookhaven National Lab. What's life as a PhD candidate for Luis? This is Luis as a PhD candidate. Turkey, Belgium, France, Qatar, the Czech Republic, and India. Of all of these, only India was actually a trip that we did with my friends when we went to go visit. But the rest of it is different conferences that I presented my work all my life as a PhD candidate. So the work, a lot of the work that I did at Brookhaven, some of it at Penn State, I actually presented at different conferences, which really enabled me to see that one, people are interested in this because you get a lot of questions. People want to see your talk. They want to see, hey, last year you did this thing with the laser. What are you doing now? What's going on? And it was, oh, this is pretty cool. Like, people actually care about it because the entire journey up until here, when I began presenting internationally, this was the first one, by the way, that was Belgium. I thought that you would go write some papers and then you would just be a professor. And that's so far from the reality because there is a whole world of traveling. So if you like traveling like I do, this is the place to be, let me tell you. So then, as a PhD candidate, I presented my work, got some more awards, did some other things. There you go. I also got another award within the GEM Fellowship as well. That was really cool. And then came graduation. This is me at the Graduate Center of Penn State, working with my advisor, Dr. Kenan Lulu. Now officially having defended my PhD now as Dr. Luis Ocampo Giraldo. So then what comes next, right? I was actually offered to be a postdoc researcher at Brookhaven because I had already been there doing a lot of my PhD work. So they said, why don't you come over? And I said, okay, let's do it. But as I was doing those 5 months, somebody from Idaho National Laboratory, we had to participate in a joint project for the Department of Homeland Security. And he said, hey, why don't you come join us? We have a lot of cool things happening, and I think you would fit right in with our group. It's really amazing. You're gonna love it. And I said, what's in Idaho? National Laboratory. I'm in New York, man, like New York City. We got beach. It's fine. It's awesome. I can fly to JFK anytime I want. And he said, well, why don't you come check it out? And I said, okay. So they brought me over for the interview. They brought my wife with me. So the two of us went, and I realized how massive this place is. And the reality is that Idaho is a Department of Energy, nuclear energy lab. So their mission is actually to push forward the entire nuclear energy R&D for the United States. And that's what they specialize in. So the world's most powerful nuclear reactor at INL. You will see some of that work coming up of the really cool things that they did. But that visit is when I realized, wow, there were so many opportunities here, and I could do so much in the world that I want, which is, nonproliferation and also pushing for clean energy. I should really come here. So then they said, well, why don't you come be a postdoc? And I said, okay, cool. But within 6 months, I was converted to be a staff scientist. So my life as a postdoc is really 11 months, which is not typical, but it's doable. It's possible because a very good postdoc will often just get converted right away or get poached by somebody. So it should be in your nature if you decide to go down this path to work really hard as a postdoc, because that's like the proving ground for you to just take off, right? So before I should have gone to the next slide. Does anybody know what this is? The white thing. Okay, let's take a moment. Raise your hand if you're a graduate student. I should have done this in the beginning. Okay, raise your hand if you're an undergraduate student. Okay, so that has nothing to do with this, by the way. I wanted to know. So I had just been converted to a staff scientist, so I was a very early career person because it was probably within the first 2 months. We get a phone call and they said, hey, we need to measure this thing. Why don't you bring all your detectors, everything you got, because I was part of the I still are, but at the time I just joined the Applied Radiation Measurements and Systems Research Group. We need to just measure this thing. Why don't you come out? This thing was at the site. From our office to the site is about a 45-minute drive. And we brought absolutely everything to do those measurements. It was out of the blue. It wasn't something planned for that phone call. That white thing you see, a few days later, got shipped over to Cape Canaveral and it was sent to space. And it's currently in another planet. So this is the only picture I have of being next to the MMRTG, the multi-mission radio thermal generator. You can actually feel the heat from the MMRTG at that distance, which is insane because never in my journey as a PhD when working in radiation detectors, did I imagine that I would be standing in something so pivotal for us as humankind, right? And that's the day that I said, the labs are just so crazy. Like crazy things happen all the time. And that wasn't the only crazy story that I have, but it is the coolest story that I like to share. So that really continued to fuel my passion for loving the national labs because crazy phone calls happen, crazy experiences happen. You meet really, really amazing people along the journey. And that was quite beautiful. So let's fast forward. 6 years have gone by. Oh, well, 5 years have gone by since that picture. So you're probably wondering, I get often asked, what's life as a scientist like? So today I'm a scientist and a team leader at the lab, as you mentioned. First, you gotta generate ideas. Now, don't think that you just I don't know, you're just hanging out, just drawing every idea you got. Oftentimes it's guided by something that the customer wants, typically whether it's an LDRD, a laboratory directed research and development idea, which is funded by the lab itself, or a customer. It could be anybody in the government, from the Department of Homeland Security to the National Nuclear Security Administration and so on. They have things that they need to get done. Somebody will say, well, listen, we need something that can do X, Y, and Z. You gotta generate that idea. That's your job. You're writing proposals because obviously you got an idea, but you gotta tell somebody how you're gonna do it and how much it's gonna cost you, right? Because you don't work for free, right? No matter what, the thing that you're gonna see is that up to this part of the presentation, during your education, you always have to get paid. You don't have to be broke the whole time. Now, let me go back, because I should have made a caveat on this beautiful slide. This is me around the world, but this is me around the world on a budget, because I was still a graduate student. So I walked, kid you not, an hour and a half to get here, right? I didn't take an Uber because I had the money for an Uber, right? I had to wake up really, really early to take the first train, which is the cheapest train to get from Strasbourg to France to actually get to that picture. And I walked all of Paris to get all the pictures that I got, right? So it's on a budget. So don't think that you're just going to be a high spender because you're still a student, but you don't have to be completely in debt that whole journey. So you still got to get paid as a staff scientist, which is why you got to write proposals. And also you gotta be in the lab, right? As you're beginning, you don't have people to help you out. You don't have people to do the experiments for you, right? You propose the ideas, right? They said, great idea, let's do it. Who's gonna do it? You have to do it. So you gotta be in the lab, hustling. There's a lot of meetings. You probably have a lot of meetings for your professional organizations today. Maybe you worked already and you saw a lot of meetings. Meetings continue to happen because as you push the boundaries of science, you now have a lot of questions. People are like, well, is that safe? Let's get together with all the experts we got to find out if this thing is truly safe. If we should operate it under those parameters. What about the waste? There are so many questions. All of that requires meetings. Mentoring. I think that at least I was given a lot of opportunities to grow into this journey that I should be doing those things too. I should be doing that mentoring. I should be offering those opportunities because oftentimes the one thing that we need when we're just getting started is an opportunity to prove that we can do it, right? It's an opportunity to prove that we could be an amazing scientist, we could be an amazing engineer, whatever it is that you want to do, you just need an opportunity. But that requires some mentoring, right? And that's part of the journey. You should build that in. Leading. You now are the leader of the group, right? You wrote this proposal, it's your idea, you're overseeing it, maybe you bring somebody in, you now have to be a leader. And it's not like, hey, you do this, you do that, and that's it. And magically, a year goes by, a fiscal year goes by, and boom, things are done. It doesn't work like that, right? Just like you might have some issues with people in your group projects, for example, maybe within your research group or something else, it never ends. You have to learn how to deal with that, and that's part of the journey. Traveling, oftentimes we're pushing the boundaries of science, or we're pushing things that are unknown, and we have to get together with other people that are pushing the boundaries in other parts of the world. Today, you can call each other on Teams and have that chat, but if you want to bring everybody together, then you got to have these meetings, and these meetings often happen in remote places. Sometimes really cool places, sometimes not so cool, like Idaho Falls, but Tokyo, Idaho Falls, publishing. Our chief scientist says that if you don't write it down, it didn't happen, right? If you don't write down science, it didn't happen. And you must write it down to then communicate it, right? You can go and make this presentation, but you have to create a manuscript. You have to create something that testifies to how you did it, how you arrived to those results, how you're pushing the boundaries of science, and that's publishing. And that goes hand in hand with communicating, right? You have to go and talk to people about why this is important, why the results you got, which might be very complex, for a lot of people, you have to, bring it to the level that people can understand and then realize, wow, this is important. We should continue to pursue that. The pictures on the left are actually foretelling of what you're about to see. This picture here is related to tripwire, so the one in the middle. This is related to the first project you'll see. And those are interns that I had last year. They're a graduate student. One of them actually just became a doctor. So Dr. Takazawa. Okay, with this, I conclude the part of my journey. Now, let me tell you about the rest of this presentation. So what is the rest of this presentation really about? We have several projects at INL that stand at the intersection of nuclear nonproliferation, nuclear energy, and safeguards. I want to highlight the importance of a comprehensive educational background in the nuclear sciences, and also the necessity of collaborative work within diverse multidisciplinary teams. And that's because oftentimes we think that you have worked in this particular tunnel of science this whole life, and then you go out and you keep on doing it, and that's very far from the truth. The reality is that the journey that took you to get that PhD or that degree has now hopefully equipped you with everything to then do a lot of different jobs, because now you're able to think critically and apply a lot of your knowledge to then solve problems, right? And combining the expertise of diverse disciplines within teams is really crucial for the ongoing development of the nation's nuclear industry. And it's paramount for addressing sophisticated cutting-edge questions, like I've said before, in the field of nuclear science and technology, right? As we're pushing the boundary forward, we cannot just be with our peers that all have the same degree. We need other people, because that, diversity of ideas and of education is super important for us to continue pushing forward. So the first project, we call it Mustard Bear. It's the multi-sensor data science system for monitoring solvent extraction processes. Anybody a chemist here? Okay, I'm not a chemist, so don't ask me chemistry questions, please. If you were like me and you were like, what's solvent extraction? Solvent extraction is just a way to put things spinning really, really, really fast in a line or in a sequence, and then taking things out. It's a method of reprocessing. In this case, we're very interested in how we can use non-traditional sensors. Well, I shouldn't go to that. Let me just finish that. Non-traditional sensors to actually monitor this type of facility of aqueous reprocessing. So at INL, we're building something that we call Beartooth, which is a test bed to study reprocessing, really aqueous processing techniques. That includes solvent extraction, like I mentioned, which is using those centrifugal contactors, which we're about to get in a second. Beartooth itself will be a glove box that will have different dissolution equipment and separations equipment, which you kind of saw already in those pictures. And the goal of the project itself is to use non-traditional sensors, and I'll tell you what that means in a second, for what we call multi-signal discovery, right? Signal discovery is anything, right? Any signal that comes out of the whole process, we're interested in. And we believe that that's important because all those signals can support the development of safeguards by design. And can also provide operator awareness of what's happening within the process and also discover any anomalies. So here's what the contactors look like. The contactor itself, the motor is the blue part that you see in the pictures, and the actual separation happens in the bottom part. You're spinning these things at about 3,000 RPM, maybe a little bit higher, and you're just trying to separate the aqueous from the organic. A typical sensor that they use is basically what makes them spin, which is a VFD. That's just how you tell the motor how far to spin. You have a flow meter because you have some pumps for the aqueous and the organic, and that's roughly it. You can probably measure the tank, the level of the tank, but everything else that you see here is something that we're trying to achieve in terms of non-traditional. So, for example, the usage of infrasound, right? Infrasound, anything less than 50 hertz, which we don't actually hear, we can feel it. So if you are in a place and suddenly a truck goes by or something really heavy happens, you can feel the vibration in your feet, but oftentimes you'll feel it in your chest. And it's not because of conduction through the waves, but rather because of infrasound is actually hitting you. So we're trying to look into that. Seismic, self-explanatory. We're also looking at conductivity, pH, temperature, and color, really an RGB probe, to see what we can tell. Why is it important? If you think about this facility doing this reprocessing, the only tools that the operators have to understand what's happening in the separation, whether it's transuranics or whatever, is really what's the flow meter at and how fast are we spinning. But in the separation, the flow sheet itself, there's not a whole lot of information. And we're trying to provide that by creating a multi-sensor system that's really data-driven to offer insights into how good that separation really is. Turns out that a whole set of tools can actually be used to infer things about the facility, which is very important because if you think about non-proliferation, so safeguards, right? A facility says to the IAEA, the International Atomic Energy Agency, this is hypothetical, not that it's going to happen, just trying to explain it to you. If a facility says to the IEA, look, we operate every day, right, 5 days a week, 8 to 5, that's it. And then they can calculate what the throughput is and things like that. But how do they verify that, right? If you are not there looking at the equipment 24/7, how do you know that they only run 8 to 5, right, 5 days a week? So if you think about that mindset, we can use that same data to actually understand what's happening within the facility itself. This is a plot looking at the infrasound data. Again, infrasound less than 50 hertz. And so what's happening here is we're showing you the RPM in the thousands to show you that when you turn on the contactors, you actually begin to see lines populate, right? So as you begin to spin at 3,000 revolutions per minute, you actually emit infrasound, right? The motor itself emits infrasound, and you can count the number of contactors that have been turned on, which is really useful because then every day at 8 a.m. you should see this line pop up, and it should have been nothing all night, right? That's the kind of mindset that we're thinking of in terms of safeguards. So we wanted to demonstrate that if you shut it off and you turn it all back on at the exact same thing, you still get the same data, you still get the same signals. If you actually decide to go above 2,000 to 2,500, you actually jump by about roughly 10 hertz to the next frequency band, and you have the same signals. And the same thing keeps on happening if you keep on increasing, right, the RPMs, to the point that you'll notice that there's a section that actually doesn't have one, they have gone really, really high, but there's no data, and that's because it has superseded the 50 hertz section that we have. That means that the detector that we have is no longer good for that, but the signal is still there. So now we have shown that we can actually see at what RPM is the facility operating these contactors, which is quite an important piece of data for nuclear safeguards. We had several students working on this last year, so I wanted to highlight some of those projects so that you can think about the type of work that graduates do, and then an undergraduate student can participate on in our lab. Here we did some machine learning, it's just a quick plot to show some correlations, but all of that data analysis was done by a graduate student. And then here's what the thermal image looks like. She put together a program that looks at machine vision to then determine what's kind of happening in the picture. So we wanted to show, hey, one, this is a tube. This is just a normal contactor, things like that. And we wanted to identify if things were too hot or not hot enough, which is also an important feature in the whole flow sheets. But more importantly, I don't know if you can see, there is a drop right there. Turns out thermal images are actually pretty good at catching leaks. Leaks are a huge problem for aqueous reprocessing. And you have an incredible high definition picture here that can actually show you the leak. You can count the leak rate, and also you can see any effects of thermal reduction. And then the picture on the right, let's see if this plays. Yes. It's actually another thermal image. You'll see that's our undergraduate intern's hand. He just waved, and it comes back down. Why do we care about this? Turns out this gives you a 1080 picture, right? 1080 resolution, super high definition. It's beautiful, but it's $70,000. And as you can tell, you can only see roughly 4 contactors. And even if you pull back, you're probably looking at only 4 contactors. Must have bear, to the part that I showed you earlier, what we're building right now, will have 40 of them. That means we're going to need 10 of these to actually monitor all the contactors. That's a lot of money for the detectors. So then we said, well, you have Raspberry Pi sensors, which is the sensor that you got on the right. If you're only looking at maybe hot, not hot, medium hot, something very rudimental, then perhaps you can make it happen with a Raspberry Pi. And that's what the intern did. Actually put together that whole picture that you see there. You can get a live video that's pretty decent resolution. And that was a summer internship program through the MSIPP. Okay, with that, let me tell you about Tripwire. Tripwire is near and dear to my heart because I have seen it from the beginning all the way to what it is today, winning awards, which I think it's a very important thing for me. But to give you context as to why we care about this. Again, think about safeguards, think about facility verification and things like that. Right now in Finland, they're building a geological repository that's roughly 500 meters below the ground. And that's what you see there in the center. The idea is that you would put spent nuclear fuel, inside of these drums, which actually, I think, it's cooler if I'm in the picture, right? Right there. So the spent fuel will go in this cassette, And this cassette will go into this copper canister, I'll get out of the way, and they will weld it together. Then they'll put it deep under the ground, 500 below. And so it's 500 down, and then they're gonna have these tunnels that are roughly maybe 300 meters in length. And then, so think about this, 500 below, you pick a tunnel, and then you go horizontal 300 meters, and then at the end of those 300 meters, you make a hole, and then you dump that canister, the copper canister, inside of bentonite, and then you just cap it, and then once you've, filled out the whole tunnel, then you backfill it. Still thinking of this, I go and ask you, can you tell me that the canister that we put there 10 years ago is still there? How can you prove it? Now, let's say, well, it's there because, we have monitored seismic things and nothing has happened. Cool. Tell me that the radiation has not leaked. Prove it to me. Then it becomes a very complex problem because, again, this isn't like, oh, let's just, open this door. Let's just, we have a vault, let's open it. This is really deep under the ground. So tripwire has been designed to actually answer that question. How can we monitor that facility? How can we answer that question X years from now? This, here I am in Finland, negative 437 meters in the ground. And I attended this trip to see how one would deploy such system. Very informative trip, but let me tell you, I think, oh, I should have gone to this. This explains it better. It's way higher definition. All right, so the machine will just bring it down. And the premise of tripwire, or long-length scintillating fibers, was originally a three-pronged system. One, you would use electromagnetic sensors, which are now a commercial off-the-shelf system that's used for perimeter security, to put it on the tunnel on each side so that you can monitor the electric field. If anything changes, which it shouldn't because it's backfill and nobody should be there, then something happened, right? Alarm number one. You can do a vibration sensor, which is also a security thing. Essentially, you just have a fiber that, by a different type of fiber than the one I'm about to tell you about, that vibrates when something is around, is making those vibrations happen. So then that reports back, and it has been calibrated to tell you more or less where it's happening. The part that we did was actually the radiation aspect, which is crucial for us because you're no longer just looking at, hey, something's happening in this tunnel, but we can actually identify whether radiation is present or not, or if it has changed, right? That's the beauty of it. So what is tripwire? Tripwire now we just call it that, even though it used to be a three-pronged system. We only care about the long and scintillating part because that's the part that we developed. You have a scintillating fiber, which is the little fiber that you see there. It's about 1 millimeter in diameter, and it fits in this jacketed tube that is also light tight. Why does it have to be jacketed? Why is it so special? Because if you're gonna backfill that with a lot of material, you need to protect your fiber, because if you break the fiber, much like if you have fiber in your house, fiber optic internet, and you mess with that fiber, your internet goes down because the properties of the fiber are gone, right? So we don't want any of that to happen, which is why we have to protect the fiber. The ability for it to scintillate or to emit light because of radiation is also obviously susceptible to photons. So the sun, light, whatever you got, which is why it's gonna be light shot. That's why it has a black jacketing on top. And then we put the connectors so that we can hot swap them very early. All we're doing in that picture is just shining the light on the other side to show you that it can also just transmit light like a regular fiber. So we wanted to show that this was possible. Typically, scintillating fibers are used for nuclear medicine in very, very small segments. They're used for actually dosimetry when they're doing some sort of nuclear treatment on you, so they put them in different parts of your body, very, very small, because they just want to do specific doses. But we wanted to prove that if you use it as a long detector, you can actually monitor radiation for the entire length of the body. That's the novelty of it. So here's what a lab looks like. We no longer have this lab, we moved buildings, but everything remains the same, still at the same tables. We use NIM-bins. Anybody use NIM-bins in your lab? No NIM-bins? Oh, good for you. We still use NIM-bins. This is how this experiment began. With a laptop, we connect everything, and then we used specific cesium check sources surrounding the fiber to then measure at different parts. The plot that you see in there on the top right is actually showing you the signal that gets picked up by the multi-channel analyzer. So in case we're not familiar, just so we're all on the same level, radiation gets picked up by the photoelectric effect on scintillating fiber. the fiber itself then emits light. Because it's light tight, the light travels, and then you can pick it up in a photomultiplier tube at the other side, which then gets assigned in the multi-channel analyzer a bit through a binning system. While the signal that you see there on the right, we just compare it to channels. So we cannot do spectroscopy, so you will not see a cesium peak because we don't have that kind of resolution. We don't have the stopping power in the sensor that we have. The fiber itself is too thin. So you have a lot of attenuation because of the long distance as well, which is why you have very high counts towards the beginning between 100 and 140 channels, as opposed to 240 onwards. And that's something that becomes even more apparent in the next slide. Because we proved that at 9 meters it worked. So then we said, how far can we go? So we said, let's build a 50-meter fiber and see what happens. And that's what we did. Here are the results showing you 50-meter fiber. We have to coil it because it was so long, showing you that data. The part that you probably care the most about is in the beginning, because that's where you can actually differentiate what the rate is, the count rate, as a function of the section, or actually as a function of the measurements themselves, towards the latter part or the farther part of the fiber, right? So we've shown that 10 meters is fine, but what happens, what's the difference between 40 meters, 45 meters, and 50 meters? And what's the difference compared to just background? What if this is just background noise? So we have to prove that, right? And this is the plot that displays that. Okay, so then let's go back to the example I gave you. You're 500 meters below the ground and you're 300. And I just show you that you can cover 50 meters. So you're probably saying, well, what are we going to do with the rest of the 250 meters and 500 meters if you're trying to get it out all the way to the surface? What do? Well, you couple it to optical fiber. Just like your internet in your house, optical fibers can go for kilometers. And the loss, the signal loss is just very, very small. But we want to improve that. So we had a little test setup where we connected some optical fiber to our scintillating fiber. Then we did some measurements to show that the loss that you have is very small altogether. So now you can have up to 50 meters in fiber of detection, ability connected to whatever distance you want away from you, from the photomultiplier tube and the electronics themselves. Anybody familiar with TRL levels, technology readiness level? Okay. Well, thank you. For the rest of you, that's how we measure it in science, well, not just science, but in technology, where we're at in that technology, right? If you just had an idea and you're like, you sketch that out, I'm pretty sure it's gonna work, that's 0. You just had an idea, right? If you do a little bit of testing, you're at 1. Ultimately, what you just saw at a lab, if you're in a bench laptop or a bench in a lab, do your experiment, you're roughly at about 4, right? Because you've shown in the lab that it works, but it's in a lab environment, you have a lot of constraints that you put there, right? That are your control. But then to get it to TRL 5, you have to have it in an environment that is alike, right? And this is what we want to do. We had promised that we would show this would work, and we would take it all the way to TRL 5 so that it was proven or shown in a alike environment. We don't have deep geological repositories in the United States. We have other things, but we just can't take them to Finland and go check it out because they're actually a facility that's working, and they're like, no, don't come here. We're not going to put your thing here. We got business to do. So then we decided to just test it out in Idaho. So in Idaho, we have out at MFC, the Materials, Fuels, and Fuels Complex. We have something called the RSWF, the Radioactive Scrap Waste Facility. And its job is actually this little section itself composed of 2 identical sections. You can tell them apart because one of them has kind of like this black mat on the ground. But they use these ISCs, or interim storage containers. And their job is to be storage containers that get moved around very often. So they bring in a new drum, a 50-gallon drum of waste, radioactive waste. We don't know what's in it, doesn't really matter for these purposes. And then they put them in here until they decide what's going to happen. They shuffle them around, et cetera, et cetera. So this was perfect because you could deploy the fiber. We put it in, all the electronics are inside of our trailer. The fiber comes out of the trailer, and then we deploy it in between the ISCs that you see there. Just to show you what the radiation field was like at the time. We had a rover or just a little, remote control vehicle, and we put a lithium bromide detector to then just do a bunch of sweeps up and down, back and forth, to show you what the field looked like, right? So from an illustrative perspective, the white line shows what the fiber looked like when it was deployed, and then the field that it was exposed to is roughly what you see here. So then they said, look, we're gonna move the ISC. We're gonna take it to the next section, and then we're gonna bring in a new drum, and then we're gonna put it in this ISC, and then we're gonna take that ISC and bring it back to where it was at. And we said, that's perfect, because hopefully we can see all of this. So there in the pictures, you see the forklift comes, takes it out, brings it to the other side, new waste comes in, we're good to go. They remove the lids, ISC first, the new drum in the middle, and then the drum, they raise it up top with a crane. You see it there in the right picture, that's the black drum that you see in there, 50-gallon drum. Then we asked them to place it back in, and then they took a picture for us. Here's the facility manager taking a picture. They didn't let us over there because it's really active. And then they took a picture. That's the new drum that was placed in there to prove that there really was a new drum. Then they closed it up, brought it back down, and all we did was ask, please put it back to the exact same location, which is why that picture is important, to show you that it came back to the exact same location. So why am I telling you about this journey? Because the fiber can actually tell you the entire journey by itself. So even if you didn't see the pictures, check this out. We have the fiber placed, and suddenly they removed the ISC. So because the radiation was taken away, you should have lesser counts, which you do. Turns out when they get it to the other side, which is roughly between where it was at to the new place is about 35 meters. Once you remove the lid of the ISC, you actually have a bit of an increase in radiation. And then they did all the checks, they have to swipe, et cetera, but at some point, you remove the lid of the new container, right, the black container, and once you raise it up top, the ionizing radiation makes it all the way over there, gets picked up by the fiber, and you can see that spike, right? So something's clearly happened. Once they put it inside, you have an elevated bit of background, then you put the lid on everything, and you drive it back, and you place it in the exact same location. So if you forget about everything between here and that light blue line, right, and you're thinking about the repository deep under the ground, something must have happened. You now have more radiation, which you didn't have before. So likely you either have a leak or somebody opened the canister. This information is crucial to answer the question of, hey, is the canister still there? Is it leaking? Is there a problem with it? We now can offer a solution with that, with our fibers. Okay, so I've covered two different projects. One about aqueous reprocessing, which is part of the nuclear fuel cycle, very important if we're thinking about the separation of transuranics or the bottom part of the periodic table. Then I just told you about a fiber, right? A detection system that goes in a deep geological repository. We're still talking nuclear, still the nuclear fuel cycle, but completely different applications. Again, I'm still participating in these things. Now let me tell you about something that I think somebody might have already met, maybe told you a little bit about, Dr. Tommy Holschuh, a colleague of mine, very, very bright scientist. The part that I want to talk about is a system that we designed to do tomography, but it's kind of a misnomer because tomography is going to happen soon. In this instance, it's only doing scanning. Let me tell you why this is important. Right now, as we think about the future of nuclear power, somebody does a lot of calculations with a lot of modeling, and they say this is the world's greatest fuel. It can withstand, pick a number of temperature, whatever, 1700 C. Don't worry, it's fine, and it emits radiation, it's going to be great. You can keep on going at it, it'll last you whatever amount of years. The burnup is X, Y, and Z. Cool. None of this is empirical because I just did it by calculations. So how do we make sure that that's safe, right? That's the job of the transient test reactor or treat. So we designed, you're going to hear about treat in a second, but we designed this system to do what we call post-radiation examination. So what they do is they take a cool fuel, they go shoot it to see what the boundaries are of that, and then they take a picture or they analyze it before it went in there and after it went in there. If you do anything to the fuel after something happened to it, we call it post-radiation examination. This is a technique for them, which is just gamma analysis or gamma spec. The system is composed of a high-purity germanium detector manufactured by Ortec, and then we have a bunch of collimators in 3 high-positioning stages that allow us to move everything around. One of the issues that we have when doing post-radiation examination is that we're creating this empirical answer of the number of fissions that fuel underwent. And to make that calculation happen, you have to understand everything that's doing the measurement, right? You have this thing that you now can measure, you know, the gammas that are coming out of it. But for you to turn that into a number of phasions and do all the math, you need to understand the detector that you're using. This is what an HPGE looks like if you haven't seen one. And so we need to do a bunch of modeling of the behavior, Monte Carlo modeling of the behavior inside of the detector. That's to understand how the detector actually does the detecting. So we take an X-ray, right? We shoot it with X-rays. We take a picture, and then we have a fiduciary, which we know is 1 inch, a real 1 inch, and then we use that to understand what's inside of the detector. Oftentimes, maybe this is happening in your lab, you have a piece of equipment, but you don't really know what's inside of it. Turns out no HPGE is identical. They're all manufactured different, and sometimes the crystal, which is the part that you have here, could be crooked, could be not symmetrical, could be just slanted, right? Maybe there are some rings that go around it, maybe they have moved, they're not in the position that you thought, and all of that has an effect as you're modeling all the particles that are interacting with it. So once we have all that modeling, we actually make the test. In this case, I just wanted to show you what that measurement was like for a 4.9% U-zirc rod. The rod is roughly this big. It's actually, well, this is just an illustration. To avoid it breaking and having a bunch of paperwork and a lot of issues, we stick it in a 3D printed container. So that way it's within that container, it's a container within a container, and we don't have to worry about anything else. And so what we do is we position it in front of our detector. I think I have another picture here showing you two things. This is what our MCMP model looks like. This is my model. And then we use that to understand the efficiency of our detector. And this is what the actual model setup looks like. So you have these constant blocks to serve as collimators, and then you have a 3 millimeter slits. That's what's allowing the gammas to come through, or the radiation to come through to your detector, and then you move, right, the rod, your new fantastic rod, you move it all across to get a scan of what really happened. What's the radiation coming out of that? So we do 600-second dwells every single millimeter that you move around, and then effectively you create a picture of what the radiation is, and that in turn tells you what happened at the time of irradiation. So you can think of this one as being a homogeneous bunch of pellets, but after irradiation, the irradiation was basically happening at the center. You can kind of see that, which is why you have more radioactivity at the center, where you have more products. And then in turn, you can make the calculation to tell how many fissions actually occur. So that's what we do. Now, let me tell you about the hodoscope. There's only two slides. There's another one about it. And that's because we're hoping to tell more about this work in some upcoming presentations, especially the American Nuclear Society, because the hodoscope is simply the only instrument in the world that can do what it does. And it just went to a whole revamping where we are doubling its capacity. Treat, this is the reactor itself. Here you have the core, has a gap in between one of the channels or one of the sides where you just don't have anything. So that the neutrons can come out and you can pick them up from a bunch of collimators. So here. Yeah, that's all I got. No, go back there. You have a bunch of collimators. And so you can think about a bunch of little squares, very, very tiny, that are all looking sort of at an angle inside of the core. With something very similar to the pinhole effect, in fact, it's the same thing. You can actually look and pixelate the core by each of these little squares. So you can see inside of it and understand what's happening in each of the little squares, or pixels as we call them. And that all gets picked up by our detector. So before, we could only see 96 channels, so roughly 2 meters and change, maybe this much. And the idea, or the beauty of this thing, is that it's the only instrument, soon to be the only instrument in the world, that can show you what happens in real time when you irradiate fuel. So you have this fuel, it's in pellets like I showed you before. It's sitting there, and now you decide to shoot it with megajoules, hundreds, maybe thousands of megajoules if you want it. What happens to your fuel? What happens to that fuel? We know that it has to balloon because the thermal energy in it is so much that you can see it actually, it has to expand, which is why circuloid, or the jacketing that goes around it, is so important, because it needs to be able to withstand that pressure. Same thing happens at an axial level. The horoscope can actually show you all of that, right? It can show you as it balloons, it can show you as it moves, and most importantly, the job of tree is actually to melt things, right? If you said it's sustained 1700, then let's shoot it with 1700 and see what happens. And hopefully it melts, that'll be pretty cool. Because then the horoscope can show you as, maybe it melts in the middle, suddenly you have a departure of, you have some material at the top, and then the bottom part of the melted just bloop, goes down. And you're like, oh, that's cool. If you don't have the horoscope, then imagine this. In the beginning, you had a cool rod, and then in the end, now you have a separated rod. You're like, here's a blob and here's another blob. What happened? How did it move? How fast did it move, right? When did it occur? Was it a 1600? Was it a 1500? Was it a 100? And I was completely wrong, right? We need that data. The horoscope can provide it to you. So I'm going to show you a video which shows you what the horoscope sees and how we interpret that data. Things that have happened before is that we actually have that breakage point where things move around, where things balloon and all of that, which is very important information for scientific purposes. So hopefully this works. I tested it early and it was fine. This is slow down. This happens in milliseconds. So let me pause it to tell you what's happening. Okay, right here. So you have a rod, much like the one I showed you before, and you've seen it in 3 pixels, and it's there. You're about to begin ramping up the energy, so the reactor's going to start shooting it with high energy, and it's going up, up. And suddenly, you're no longer looking at 2021. And at some point, you only have it between two, and you're like, what's happening? And then, it shows up at the bottom, which means we can now quantify the movement of that, because that fuel actually moved, right? Something happened to the structure of that fuel and it actually shifted down. It fell, right? Whether it fell because of the, the test holder assembly that was in it, or because the fuel itself melted, all of these things are important and the horoscope can see that. So that takes me to my last slide. Very good timing, 40 minutes. No. Am I past time? Am I good? Okay, sorry. One, I want to tell you to cultivate your curiosity, right? The reality is that you're here, you're very bright, you got what it takes, and if there's something you're curious about, pursue that, because you need to find what you're passionate about, and that's a very long journey. It's a hard journey. It's not an easy thing. You always have to work hard, right? Our lab director says you create your own opportunities, and that includes working hard. You got to work hard to find those opportunities, to find something that makes you very excited, right? You have to embrace failure. Failure is everywhere, especially in science. Science can be very cruel. You have weeks, months of an experiment, and then it sucks because your idea sucked, or maybe just because something else happened, or somebody dropped the ball. That's okay, right? That's life, that's science, and embrace that, because then it makes it less hurtful altogether, and it's never gonna stop, right? And that also happens with proposals and so on. It's just a difficult avenue altogether. And that goes in hand with being resilient, right? If you're facing adversity, then be resilient and keep on going, keep on pushing hard, right? Don't doubt yourself. Imposter syndrome is real, that's okay, but you can navigate it. Know that if you're here, right, and you're doing hard work, this is the right path. Lastly, remember work-life balance. I think it's very easy for us to fall in love with science, with our work, with our job, and we forget that we have to take care of ourselves. Whatever that means for you, don't let that go. It's important for you to take care of yourself, to do the things that you enjoy, and don't just focus on science and research and getting your PhD or your graduate degree or everything else, okay? And the last thing, your education does not determine absolutely what you're gonna do, right? It's the journey and everything you learn, or the tools that you learn to get there, or when you finish, that will now enable you to do whatever you want. Whether it is putting or helping put an MMRTG in another planet, designing the next, or helping test a new set of fuels, right? New nuclear fuels, or a whole new set of tools that you never worked with, like in my case, an infrasound. That's never what I did, but everything that I did enabled me to be familiar with it and continue to pursue it as a scientific domain. You can do that too. So with that, thank you so much. Really appreciate your time.
All right, I'm gonna open the floor to questions. Jaden?
Hi, I'm Jaden Brewer.
Jaden.
The question I have is, when you are trying to communicate your science to like policymakers, how do you go about that, and how do you convince them that the science is real and that they should do certain things?
Yeah. It's a very tough question to answer because oftentimes it depends on the audience because it even changes at that level. A lot of them actually have been scientists at some point in their life, so they're very familiar, but a lot of them have no clue, and that's why you have to go to aspects of saying, listen, think about this mindset, right? Because a lot of people don't understand safeguards. Why do we care about nonproliferation? So just conveying that context is the first step, because if you don't have that mindset, then you're like, I don't really care if you turn the contactor at 1,000 RPM or not. Like, it doesn't matter to me. Like, no, if you look at it through these lenses, then it makes a lot more sense. And oftentimes finding that middle ground, that common ground with other people is probably the most challenging aspect. And you have to just try until you find what works for you, because oftentimes our styles of communication are really what makes everything click. And you have to learn that by yourself.
Yeah, do you find that they are like, I guess, willing to change their mindset to like
Yeah.
get in that mode with you so they can start like,
I think as humans, we're all susceptible to seeing like real data. I think real data means, oh, look, it was blue, now it's green, like something changed, right? If you can apply that to show that the data is showing that, and it's not just you making it up because you say, oh, I have 30 years of experience doing this, and blue means this, and green means that. Like, no, if you actually show the data and it's very apparent, or you help drive that message with it, I think that goes a long way.
thanks.
Thank you.
I had a question. You showed that graph with your 50-meter scintillating fiber, and there was a peak that wasn't necessarily at zero. I was wondering if you could explain to people about that.
Absolutely. So I love putting that in because everybody, if you're paying attention, you'll see it. So the peak is actually omnipresent every time you have the system running. What we did is actually run the system without the fiber and with the PMT, and the peak is still there. So we believe we don't have a way to test it without just the PMT, because then no signal will come in, so the MCA will work. But we believe it's an artifact. We have shown that it's an artifact of the test setup itself. So I don't have the data to show you, to prove it to you, like I just said, I should prove it to you. But when we did the field test, we used completely different electronics, so it was actually the NIMBY's fault. If you take the NIMBY out and you just use modern electronics, you don't have a peak fault. Yeah, it's just an artifact. Thank you. Jane.
I was curious, you mentioned trying to detect if there's a change in the levels deep underground there, but what would you do if you actually did detect some sort of change? What would you do there?
Yeah, so it's an interesting question because it's outside of our realm, because we're not the owners of the facility, we provide the technology. Likely, the goal is that you know exactly what tunnel and what casket is, so you can get to it very easily, because now you don't have to dig out the whole thing. The bad is that you have to dig it out, and then that you have to prepare for absolutely anything. But the silver lining in this is that now you have an actual set of data to tell you what's happening, whether the radiation has migrated, because maybe you have another set of detectors somewhere else and you're picking it up there, or not, right? As opposed to you just not knowing about it, which would be a huge issue. Or you find out about it because your water now, and made it to the water table, and now your water is radioactive. That's a huge problem, so, yeah.
You guys start your hand up.
Actually, that was part of my question. So I wanted to know how safe it was, if what's actually happening geologically.
Sure.
I'm not sure who the tribal people in Idaho are, because it's but I was just wondering, geopolitically, do y'all have relations with the native folks of that land? What do they say about how y'all storing these?
Yeah, so let's make two distinctions. One, the Deepa Geological Repository is in Finland. We're likely, it would be great if we have it, but we're unlikely to see it. Yucca Mountain was our attempt at that, but we're not gonna talk about it. We're just really that. So we don't have that. The waste that we have remains in the upper right atmosphere, so it's not actually going on the ground. Sorry, I shouldn't say the upper atmosphere, it just remains there. And then it gets moved around to other actual waste repositories like WIP, which is in Carlsbad, New Mexico. To answer your question about relationships, it's the Shoshone-Bannock, yeah. And then we have a lot of ongoing efforts. One, to provide transparency on everything that we do, and also to get them to participate in the research, to really become scientists on it, which I think it's a really worthy endeavor. Your first question was about how safe is it? in order for a lot of these countries to prove to their own public that it's safe, they have to conduct a lot of work. In fact, the Germans have spent about 3 years already worth of geologists' time looking at every possible section of Germany where they can put these things. This the geological hospital. The Finnish did the same. Turns out that's actually a little island. The whole thing is more or less bedrock, and it's all surrounded by bentonite. Bentonite absorbs water and it grows, right? The idea being that if you have some sort of leak of water, then you won't have any transportation of the cast or any, corrosion, but rather you just seal it right away by the bentonite itself.
We have time for one or two more questions. Go ahead, Nick.
Hi, so with the current setup of tripwire, how do you, one, test the reliability, make sure your probes are still working, and two, if they do break, how do you fix them? Do you just pull out
Yeah.
you have to dig it out, or is there gonna be a conduit that you can pull all the fibering out, reattach it, kind of drop it in?
So since it's a fiber and it emits light, you can actually put an LED on the other side, and you can just query it however you want, every day if you wanted to. And the signal should be the same because, you're not losing anything. So if it hasn't broken down, then it should return the exact same signal of whatever you shot on the other side. If you break the fiber, which I think is very unlikely to happen, if you do it, it will be an installation because somebody stepped on it or like bent it the wrong way, then you will replace it. If you break it, once it has been placed in there, then let's see. You could probably open the jacket, take the fiber out, and then find a way to spool in a new set of fiber. Yeah, but truthfully, I don't think that's likely to happen. We have had scintillating fibers or just plastic fibers since the 70s. So the lifetime of knowledge that we have of behavior and laws of fibers is over about 50 years. And it's not much, right? You're not exposing these fibers to very, very high radiation, so browning is not going to be an issue. I think you're more likely to have electronics fail because they're electronics. And the beauty of the whole setup is that, remember, we're taking it all the way to the surface so that at the surface, you can just get a new PM2 and plug it in.
So you mentioned about maintaining the work and life balance.
Yeah.
And earlier you spoke that you have a wife, so it clearly shows that you're passionate about what you do. So how do you maintain the work-life balance with your family?
When I go home, I start talking about work and I start thinking about work. Yeah.
But even with that, like when you're thinking about, you like turn it off like that, even though like your thinking still is in your head, what goes on, you still think about your research, or
Yeah, absolutely.
completely just.
Oftentimes, you might go home and realize you experiment after several weeks. This isn't just making it up. This has happened. It just failed because it sucked. And you're like, what do I do? And you're so defeated, but you still gotta go home, and it's not your family's fault that it sucked, right? So you're still thinking about it, but it doesn't mean that you're not spending time with them. So you can think about things like that. The problem is when you continue to work at home, right? And you're no longer just enjoying your time at home with your family or significant other, but you're just, continuing to work. And it's kind of like you're working, 14-hour days like that. That's not healthy.
All right, can we take the speaker one more time?
So we stop this.